All right, chapter 11, section 4. One more to go. Chapter 11, section 4 is called limits at infinity and limits of sequences. Let's go. Get it open. All right, so the first thing is, let's talk about end behavior, okay? End behavior is describing the ends of your graph. So the left-hand behavior, the right-hand behavior, okay? We're going to use limit notation to describe it. So in previous sections, like when we did this a long time ago, when we did this at the beginning of the school year, and we talked about end behavior, you were talking about a rational function, something that had, or polynomial function, sorry, that had zeros, and we would look at our highest exponent to see what happens at the left and the right-hand behavior, right? We would say either they both go up, they both go down, one goes up and one goes down, that kind of thing. So now we're just going to use limit notation to describe that. And we do this mostly with rational functions. So if you look at the one that's here, I'm not focusing on the middle part of this graph. I am focusing on the ends. So I'm talking right end and left end, or how it starts and how it finishes. Okay, and we're going to use limit notation to talk about it. So if you look at the x values as they go to negative infinity, I'm saying look at what's happening at the left portion of my graph. What's going to keep happening as those x values get smaller and smaller and smaller and smaller and smaller? What happens to the y values? They are also getting smaller and smaller and smaller, but there's an asymptote there, right, which stops them from crossing the x-axis. So these values are going to get smaller and smaller and smaller, but they are really just going to get close to 0, and they never cross 0. So the way we would say that in limit notation is I would say the limit of whatever this function is, so if this is f of x, as x approaches negative infinity, f of x equals 0. So when I'm talking about the left-hand behavior means what happens when my x values approach negative infinity. In this example, where there's a horizontal asymptote, those values are going to get very, very close to 0, but never actually hit 0 because there's an asymptote there. If you look to the right-hand behavior, now I'm focusing on what's happening on the right here. My limit notation would look like this. The limit as x approaches positive infinity. And what's happening to those y values? They're getting smaller, 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 but they will never hit 0. So they will approach 0 but never hit 0. So I would again get f of x equals 0. So on the left and the right hand of this graph, both your values will approach 0 but never hit 0. So the limit of the graph is 0. So you can read these from a graph, and you can also read these from an equation, okay? So in this question, it says from the graph, use the end behavior of the rational function using its graph. So look at my rational function. They plotted it for you. So my equation is f of x equals x plus 1 over 2x. And what's happening that y equals 1/2 is what? What is on this graph, what is y equals 1/2? What is that dashed line? Horizontal asymptote. So what's going to happen as my left values, or as my x values approach negative infinity, they're going to get closer to that asymptote, which is at 1/2. So the limit is 1/2. And on the right-hand side, what's happening as the x values get bigger? Also getting closer to 1/2, so the limit is 1/2. You're literally saying that the end behavior would be the horizontal asymptote. It's basically the entire concept, okay? And we can find the horizontal asymptote visually, like in this example, your horizontal asymptote is at 1/2, or we can review all the rules of our horizontal asymptotes. So let's say I didn't have a graph. Then the way I find the horizontal asymptotes is one of these 3 ways. A horizontal asymptote occurs in one of these 3 ways. If you have a rational function, so if it said x to the n over x to the m, n is the highest exponent in the numerator, and m is the highest exponent in the denominator. So the first thing you want to identify are those two. What's the highest exponent in the numerator? What's the highest exponent in the denominator? And then it's going to have one of those three relationships. If n is less than m, so if the highest exponent in the top is less than the highest exponent in the bottom, then there's a horizontal asymptote at y equals 0, and my limit on both sides would be 0. If n equals m, then the horizontal asymptote occurs at, the y's over here, but it's y equals the leading coefficient of the numerator, so the number on the front of that x with the highest exponent, over the leading coefficient of the denominator, and the limit on both sides would be that value. And then the third is if n is greater than m, and this is where no horizontal asymptote occurs, and there would be limit does not exist. There would be no limit there. So if there's a horizontal asymptote, then the horizontal asymptote is your limit on both ends. If there is none, then we say the limit does not exist. All right, so again, this is basically what I just said. If the rational function has a horizontal asymptote, the limit as the function approaches infinity or negative infinity is the horizontal asymptote. And if there is no horizontal asymptote, then the limit does not exist. It would go on without bound, so that's why it would be the limit does not exist. All right, example 2, find the limit as x approaches infinity. If it does not exist, state DNE. Notice it just says positive infinity, so we are only working at the right side of my graph right now. If it said negative and positive infinity, then it would be both ends. So the limit as x approaches infinity is how I would write it. Now look at A. What's the highest exponent in your numerator? 1. What's the highest exponent in your denominator? 2. So what's true about n and m? N is less than m, and if n is less than m, then your horizontal asymptote is at 0, so the limit is 0. Go to B. What's the highest exponent in the numerator? 1. Highest exponent in the denominator? 1. What is true about n and m? They are equal, and if they are equal, we do what? 2 over negative 1, negative 2. Easy stuff, yes? All right, example 3, same thing. Find the limit as x approaches infinity. So the limit as x approaches infinity. Highest exponent in C in the top. 2 in the bottom. 1, what's true? Does not exist. Good, n is bigger than m, so the limit does not exist. And D, x high, first we have to do what here? This one requires some work. I gotta combine them. I gotta get them into one equation. So how do I add these? Good, and then I gotta give it a like denominator, so I'd have to do what? Multiply both of these by x squared, and I get 4 plus 3x squared over x squared. Now what's true about n and m? They are the same. So where is my horizontal asymptote? No, it's just x squared. Because you multiplied this, not add. Yeah. What would be your horizontal asymptote? 3 over 1, which is 3. Still good? All right, so now we're going to use a limit to find sequences. So this is almost the exact same thing. It's just a different format of the question itself. So if you remember your sequences, this said something like a of n equals, and then you had some sort of sequence, 3n plus 1, or a of n equals 2n over 3n plus 1. These are all sequences, okay? And when we did these, this is, what chapter is this? 8. This is chapter 8? Yeah. When we did these, we narrowed it down to then arithmetic sequences and geometric sequences and all that stuff, okay? You don't really have to worry about that. What you do have to understand is it's going to ask you to find a couple of terms, like find the first 4 terms, find the first 5 terms, and then notice what's happening to your values. So as you plug in 1 and 2 and 3 and 4 and 5, what's happening to the result is what you want to notice, okay? As the n increases without bound, which means I find the first, then the second, then the third, then the fourth, then the fifth, and I could keep going. The terms of the sequence are going to get closer to a value. That value ends up being where your horizontal asymptote would be, which ends up being your limit. The words that we say there, so like when you see the word converge, it means that that sequence it's said to converge at that value. So if as I keep plugging in values for my n, my values of my output are getting closer to 3, for example, then we would say they converge to 3, and 3 is the limit of that sequence. But all the rules about horizontal asymptote still apply. So you could also just look at your function and use the rules we just went over to figure out your output, okay? And then figure out your limit. So example 4 says find the first 5 terms in the sequence and then use the terms to evaluate the limit of the sequence. Assume n begins with 1. So we're going to plug in 1 for n. Then we're going to plug in 2. Then we're going to plug in 3. Then we're going to plug in 4. Then we're going to plug in 5. So first 5 terms. So this is 2 times 1 plus 1 over, guys, 2 plus 1 over 5, 3/5. Then repeat it where n is 2. 2 times 2 plus 1 over 2 plus 4, 4 plus 1 over 6, 5/6. Plug in 3. 2 times 3 plus 1 over 3 plus 4, 6 plus 1 over 7, 7/7, which is 1. Plug in 4. 2 times 4 plus 1 over 4 plus 4, 9/8. Plug in 5. 2 times 5 plus 1 over 5 plus 4, 11/9. So as we look at these values, and God bless you, and if we had continued to plug values in, you would see them continue to grow, but they are growing by a smaller amount. They will eventually converge and stop growing so quickly. Look at your original function. What value do you think they are approaching? What's true about the exponent in the top and the bottom? What's true about the exponent in the top and the bottom? They are both 1. So where would the horizontal asymptote be if I graph this? 2. So if I kept going with my n values, I would get closer to 2. I would never bypass 2. I would never hit 2 or bypass 2, which means that the limit is 2. So the limit as x approaches 0, or infinity, infinity, of that 2n plus 1 over n plus 4 equals 2. Look at the exponents. Go back to your horizontal asymptote rules. Go to your exponents. They're the same. So it's leading coefficient over leading coefficient. So you can use the rules from before. You could also, like, if it kept going, this one you don't quite see. You know it's past 1, so it's not going to be 1 where your limit is. If I kept going with my n values, I'm going to keep getting closer and closer to 2 and never actually hit 2. Yeah, except that it also wants you to find the first 5 terms. Yeah. All right, you do B. All right, your values should have been 3/5, 5/8, 7/13, 9/20, 11/29. So these values are getting smaller, okay? And if we go off the rules of our horizontal asymptotes, If we go off the rules, the exponent in the top is less than the bottom, which means the limit is where? Good. Questions on anything we talked about today? Okay. WebAssign is open, but again, we're doing 2 days. So if you have it, you want to wait till tomorrow, you can work on it in class tomorrow. Tomorrow we're going to do the warm-up and then that guy. Okay.